Welcome. Good morning. Let me bring up some notes here for us. I just got to sit down in front of my computer here. So, all right. Okay. Try this again. Try. Why is this not recognizing my flash drive? Yeah. Having technical difficulties here. Let's see. Come on now. Why is this not? So I'll put it right here and see what happens. All right. I think I found it that time. Let's see. Now, let's see what we got here. All right, that's not the first section. I'll go switch over to that one. All right. Let's see. It looks like we have two wonderful people out there with me here. So, yeah, I kind of was wondering what how many would show up for this live lecture today, being the last day of the exam period. But that's all right. We're going to plow right on through, and I guess you're here. That'll save you from, you don't have to watch the video later, unless you wanted to watch the video later, of course. But you'll get to see it live and in person here, and I'll have it recorded for everyone else. So, all righty. So let's get the show started here. What do you say? We're going to, let's see. Can you hear me okay out there? I just want to make sure if I start talking or.
Yes, sir.
Okay, thank you.
Yes, I can hear you.
Beautiful. Oh, yeah, there we go. Oh, we gained a person. I love it. All right, so, let me see. I'll go over here for a second. Something came up in the chat, probably saying, yes, they can hear me, or, yeah, okay. Very good. All right, so let the games begin. Now, this section is going to be a kind of a continuation or expansion upon this thing we called the conditional probability last week. I'd made an announcement in Blackboard. It was only a little while ago, so if you didn't see it, that's okay. That this might be a little confusing if you didn't see the conditional probability, either attending the whatever live or show live or watching the replay of it. So kind of hang. If you know that you didn't do it, then in other words, I guess what I'm saying is if it kind of confuses you a little bit, that's understood. If you haven't seen that, so all right. So we're basically still using the idea of, using the probability of an event occurring given that we know some other particular event occurred. So let's take a look at these conditional probabilities from 4.2 and let's see what's going to happen here. Let me change this view bar, get my tools going. Okay, now. All right. Now let's look at these conditional formulas. So P of B given A will be P of A and B together over P of A. We learned last week that the denominator is always the one that's on the right side of the conditional. And that vertical bar means such that, or given, or the if, that sort of thing. We talked about that when it's not mathematical. Like, it doesn't mean divide or anything like that. And then you see if you reverse the order, it makes a lot of difference. It doesn't make any difference in the numerator, but what makes it different is the denominator is different. So that makes the result different. So same numerator, but now it's the one that's on the right, so it's P of B. Now, doing a little algebra trick here, but you don't have to actually do this yourself because it's already developed here. But if you take the one on the left here and you brought the P of A up to the numerator, put it beside it, just basic algebra. Nothing fancy, move it up over. You have multiplied both sides by this. So if you take this, now you can say that P, A, and B equals this result. P of A times P of B given A. And then if you take this and move it over to the numerator, in this formula, you can say that P of A given B equals P of A times P of B given A divided by P of B. So you see, we're using information here. Like I said, it's going to have to give us information that yields something where P of B given that A occurred, but to find it the other way around, to give A given that B occurred, we're going to need a formula to do that. So, so let's kind of jump down in there now. Now it's going to get a little more advanced here than this on the bottom because if you have more than one way that can lead to. Let me open up 4.2 just for a second here. Might want to refer back to it periodically. So we learned like last week on a tree diagram. Yeah, okay, this one's fine right here. That this marginal probability rule, that the P of A, and you have to look at everything that leads to that particular, like this one. So the P of R2 might not be a single value, might be something we have to calculate. So it would be everything that leads to R2. So the way we did this last week is we would have said that, all right. To get to find P of R2, we would have multiplied this path, R1, R2, and these are conditional probabilities over here. And then W1, R2, we'd have multiplied along that path. Then we would have added that result together, and that's exactly what happened right here. Okay, so now let me switch back. That's what's going on here. Is we often, have two cases. I mean, this is three or more cases. We're not going to let this get too long and messy in that denominator, but theoretically, if there were a bunch of ways to get to whatever you were trying to find, you could have a bunch of paths to have to multiply together, but we're not going to let it get that severe. So you see what happens is the denominator expands. If you've got two, like this is two ways to get to B this time. You can get from A to B or not A to B, meaning it has a complement. Now, there's three or more cases. I mean, it's not just it's like three different, like it says A1, A2, A3, or it could be three separate letters. Like, let me sketch something just real quick here. I'm going to bring up a blank page here. And they don't have to be, it's not necessarily these letters. They don't have to be A1, A2, A3, but like suppose you had, let's see. I'm not going to make this look real pretty here, but here's an A, B, and a C. So you can see that one, if you're trying to get what D was, you see there's three paths that lead to D, right? A, B, and C go to D. So you would then have to multiply, along each path that gets to D and then add that up. So like I said, theoretically, it could be a lot more, but I think in our world, it's safe to say we're not going to let it get too rude there with too many of them. So, all right. It's okay. So we got to kind of, yeah, it's hard to really make much sense of these formulas because the math is not hard, obviously. It's just kind of multiplying and adding numbers. But figuring out what number represents what, that's probably the primary challenge of this, is figuring out what number goes where, you know. So, and that's what let's look at some examples that I have here, and we'll kind of carefully walk through these. And then, of course, I haven't looked at my math lab problems, so I'll try them along with you, but we'll jump over and certainly take a look at those too. Well, let's look at some examples that I've already come up with here. I found from other sources online that I worked them out myself. Because you know, it's you got to figure out what's going to be on what part of the tree, and let's see what's out. Okay, so first of all, now we've got two boxes that contain red and green balls. The first box has 4 red and 2 greens. And the second box contains 4 greens and 2 reds. Now it says the probability of selecting box 1 or box 2 at random are 1/3 for box 1 and 2/3 for box 2. Now, we got to figure out what goes in, you know, what's the proper order when we draw this tree. That's, you know, do boxes go first or do the balls go first? Now, last week we had the one with just balls, there were no boxes. So you can see that's what I was talking about, this kind of an expansion of what we were doing last week. Now, if you look at this, if you know what box it came from, you can figure out the probabilities, right? If you know there's 4 and 2 here and then 4 and 2 opposite colors in the second box. So the path has to start with the boxes first because we can figure out the conditional probability. For example, if this one has 4 red and 2 greens, we know there's a probability of 4 out of 6 that we chose a red ball if we know it came from box 1. So that tells me that that's got to be the conditional. That's got to be the second part of the tree, and then it sprouts out from each box here. So you use whatever letters you want here. I'm just letting you know this is the lettering and naming that I'm choosing for each of these events. And then we'll get back to the question. Let me explain the tree, and then we'll look at the question that was asked. All right, let's see. So it gave us the box 1 and box 2. Actually, keep in mind, and we'll see this later, it really only had to give, if there's only 2 boxes, it only had to give us one of those 2 probabilities. Because I mentioned last week that the branches have to add up to 1 on the tree. So if they would have told us 1/3, then the other one would obviously had to have been 2/3 because there's only 2 choices. Now, if there's more than 2 choices, we would have needed more information. But in this case, knowing one box would have been fine. And then because in the first box there's 4 reds and 2 greens, we have 4 out of 6 chance that it was red given it came from box 1, and then a 2 out of 6 chance that it was green given that it came from box 1. Down the bottom route going box 2, that one has 2 reds and 4 greens. So you have a 2 out of 6 that it was red given that it came from box 2, and then a 4 out of 6 that it was green given that it was box 2. All right. Let's come back up here and see what it's asking, the question. Given that the ball selected was red, what's the probability that it was selected from the first box? So as I mentioned last week, you got to be careful is that, you know, if the given part is listed at the first of the sentence, it's still the part that goes after that line in the formula. In other words, this could have been worded this way, or if you reverse the sentence around, it could have said, what is the probability that it was selected from the first box given that it was red? That means exactly the same thing. whether that was at the front. It's the part that attaches to the given that goes second, and the part that attaches to the probability wording that goes first, no matter the order that it's presented in the sentence. So be real careful with that. All right. Let's see. Now this says get rid. So here's what it's asking. It's asking box 1, given that we know it's red. See, if it would have asked what's the probability that it was red given from box 1, game over. It just would have been 4 out of 6 right there. But that's what you're going to see in these problems for the Bayes theorem. You're going to see conditionals that are worded as the probability of the first part given the second part. That's really what makes this a Bayes type of problem. Yeah, other way around, it's kind of game over. So we're going to use a modification of this formula right up here with the just using the lettering that I'm using for this problem. So that's what we're kind of working with right there. But technically we're working with this one really. Well, because we've got two ways. Yeah, we're going to be using this one really because there are 2 ways to get to it. My fault. But anyway, there's 2 ways to get to. Yeah, you'll see. Yeah, okay. I wrote it. I didn't scroll down far enough, but it would be P of B1 times P of R B1. So we need to know that number, and we do have that number. That's the 4 out of 6 divided by the probability of R. But see, the probability of R, there are 2 paths to get to R. So however many paths there are that get to R, that get to whatever you're looking for here, have to be multiplied out and then added together. Now, if you get kind of comfortable with this, you don't have to really, if you realize what's going on, you don't have to worry about the formality of how you write that out on the bottom. And as long as you realize, okay, I just got to take everything that goes to R. B1 goes to R, multiply. B2 goes to R, multiply, and then add. So you can kind of try to help you simplify it a little bit if that helps, where you don't have to get too bogged down in the nut. But I wanted to, as the instructor, I wanted to write it out with the proper notation. But if you don't, that's fine. Now, and then the top one is B1 R times R B1. Now, here's something interesting to note that whatever's on the numerator, when you have one of these ones that have several of them, 2 or more added together, the one that's on the numerator is going to be always part of the denominator. You see, it doesn't have to go first, but it's always going to be part of it. So the fact that this one was on top, guaranteed that one's going to be on the bottom. So B1 times R6, R1, 4 over 6, which is R, and then P of B1 is 1/3. So you have 1/3, 4, 6, and another 1/3, 4, 6, then 2/3, 2, 6. Just do the arithmetic, and you end up with the answer is 1/2. Which, you think, well, because it's kind of, it's factoring everything in there, well, there's more reds in the first box. That's true, but you're also factoring in that there's less reds in the other box, and all that, is computed. You don't have to overthink this by any means, but some people might look at it and go, oh, that should be higher than 1/2, but no, it's that works out right, because it's also considering the other probability that you went the other route. So the answer for that one then just worked out to be 1/2. So let's see. Let's keep trying here. This is part B for the same scenario. Given that the ball selected is red, what is the probability that it was selected from the second box? Okay. Also ends up being 1/2 here, but well, let's look through the calculation setup. So it's P of B2 times P of R B2, then over P of R. So now we need everything that leads to R again on the bottom. But if the only difference here is what's in the numerator this time. The denominator is exactly the same because it's using the same P of R that we used before. Now, the numbers were in a different order that I had before. The 1/3, 4 over 6 was first, I believe. Yeah. See that? But now notice, because P of B2 times R of B2, that's this right here, that is now the new numerator instead of this. So that one just happens to, okay, and it's mentioning that here is what I was sort of saying. That one ends up being 1/2. I don't know if I'm never going to really ask you a question about comparing it. Well, I'm not, but you know, my math lab might. So let's say, so they're telling me there's more red balls in box 1 than box 2, but then it kind of evens out because the probability of box 2 is higher. And it says Bayes' theorem takes all that into consideration. So, but just, you don't have to think all that through yourself. Just if you get it set up right, put the numbers in there, you should have no problem. Let's take a look at this one. But this has all kinds of, the Bayes' theorem stuff has all kinds of, you know, business applications, and especially like in marketing stuff, you know, you can use it to test sort of items, you know, based on, I saw one example, I didn't use it, but a TV based on something or another, and then they'll try to calculate, well, what's the probability that, you know, they like this TV given that blah, 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 sort of thing, and can provide useful information. Let's see, light bulbs. We got 3 factories, A, B, C, 20%, 50%, and then 30%. %. Okay, well, they didn't, separate sentences might have been better, but every one of these things are all attached to this, you know, 2% of the bulbs in factory A are defective. 1% of the bulbs in factory B are defective. And then 3% of the bulbs produced in factory C are defective. Okay. Now that's so what does that tell me? That's, you know, as far as how I set up this tree. That is telling me that, I'll just use the first one for example, that the probability of defective is 2% given that it came from factory A. Given that it came from A. So what does that tell me? That tells me on my tree diagram, the factories will go first, and then whether defective or not defective will go second. It'll be after the factory because of this information that's given to us. Now, obviously, we got to have the information that we can put on the tree, and that means the question it's going to ask is going to reverse it the other way around. So you see, yeah, it's going to reverse it. This also tells you, so that what is it, given that it's defective, what is the probability that was produced by factory B? So probability of B given that it's defective, that kind of means on the tree, it will be the opposite. The factory will go first and the B will go second. But anyway, so, okay, I'm just using, you know, whatever notation. D for defective and D prime for not defective. And there are those 3 probabilities of what factory it comes from. There's a 20%, 50%, and 30%. Here are the defective probabilities based on what factory they came from. So we have the probability it was defective given that it came from A was 2%, so it's 0.02. Probability it was defective given that it came from B was 1%, 0.01. And then the probability it was defective given that it came from C was 0.03, 3%. So writing those out kind of then can, oh, I mentioned we don't even need a tree. Did I? Well, I'll tell you what, I'll draw the tree anyway. Oh, okay, I'll show you why we don't need one, but I can draw it because we don't really need all the non-defectives. But yeah, I think I'll just go to a note page and sketch it for you anyway. Sometimes that will happen with these problems is you won't necessarily need the tree because it will have every bit of information that you need given in the problem. So even without the tree, we can write this out. So the probability that it was defective and probability of B, probability it came from B given that it was defective. So up the top, that's going to be the probability of D given B, the reverse of this times B. And you see that one was always going to be part of the bottom. It didn't have to go first. So essentially it's everything. It's P of A times D given A plus P of B times D given B plus P of C times D given C. I think I will. I'll draw the tree. Let me go ahead and just finish this real quick because that might help you visualize this better. So let me do that. I won't add it to the notes, but obviously somebody that watches this live or if they watch the recording, they'll see me draw it. So there's B times D given B is 0.5 times 0.01. And then it's just these three pairs all multiplied together go on bottom. And you get 0.005 divided by 0.018. And this answer was exactly the answer they had from the source I got it from. So 0.2778. So yes, let's go ahead and do that. Come over here. This will be my scribble page here. So we'll come down here and just reduce this a little bit. All right. So I've got 3 BC. And they're 20, 30, and 50. But I can't remember what memory's bad here. No, wrong section. 20, 50, 30. Yeah, I would have got it wrong. So what I like to do, and you'll see in these other problems later, is always put the stuff I know in red, and then if I add it, I'll use a different color. And then these percentages here were 2, 1, and 3. Okay. Now, to solve this problem, which actually I could add another problem right here on this page to this, but it didn't give us these other ones to complete this tree. But let me go ahead and do it anyway, because all we needed was everything that led to D. See, so that's why it had all the information we needed. But let's look at it this way. Let me go ahead and do these. I'll just use D. Not defective means okay. We can get those numbers pretty easily because the sum of the branches for any probability tree must always add up to 1. So I can complete this, even though I didn't need it, but I think I'll now ask a question that uses these numbers. Oh, I see it. I see it. Don't yell at me. 98 was the first one. This one's 99. I just started writing the same number every time like an idiot here. 97 and then 97. So you see how each of those branches add up to 1 now? So even with the information that we were given, just that information alone, we could have asked, let's see, that was coming from B. I'll say, what's the probability that it was not defective? No. Sorry, wrong order. What's the probability that it came from factory A if it was not defective? Came from A given not defective. Notice the problem, like I said, the problem original wording had no information about the not defectives, but you see what I just did right there, I was able to complete that rest of that tree. So I could actually answer this question, and I will. So we're going to have, on the top, it's going to be just the stuff that relates to the D. So it's going to be probability of A times probability of D prime given A. On the bottom, it's everything that leads to D prime, which is A, B, and C. So this one's always, this was going to be there. And then we have B. D prime given B plus P of D prime given C. Oh, times P of C. I'll just put that, I didn't have to put it first, but I will just to be consistent what I'm doing. Let's put the numbers in there. So A times D prime given A. So it'll be 0.2 times 0.98. Plus B. Somebody's mic. Somebody might need to turn on.
No, I had to guess. It was a guess. I heard without counting before because without means power.
Nào tôi bút thi vào tổ ta đấy cả đấy. Một số thằng cái chân này phải gần hải ơi, phải bắt cái chân phải đi một cái này chắc còn có
I swear to God.
I think someone needs to turn off their mic. Please turn off the mic. Okay. All right. All right. So 0.3 and then times 0.97. So I'll put that in the calculator. Oh. 0.3 times 0.9. Like, I forgot it myself. Nope, 0.2 times 0.98. I'll be over there to the chat in just a second after I finish this. 0.2 times 0.98. Now, if you do this all in one step, be careful in the calculator that you need to wrap parentheses around the denominator so it keeps everything in the bottom all tidied up there. Plus and 0.5 and 0.99. Plus 0.3, I guess that one has to be 0.97, but let me check. I do remember that being one of the numbers. No, God dang it. Wait, oh, it's my scratch page. What am I looking for here? Yeah, 0.97 times 0.1996 or whatever. So about a 20% chance of that happening. So, all right. Okay, so let's come over here for a second. And, oh, about the mic. Okay, that was about the mic thing there. All right, we got that resolved. That's beautiful. So, all right. All right. Back to where we were. So I just wanted to show you, so obviously it's got to be, it could ask something that it didn't give us, but it's got to, construct, we have to be able to fill in the tree to get it if we needed that. But that's what I was saying. We did not need it for what it originally asked, though, obviously, but we certainly did if it would have asked for the not defective. But, it's not a bad idea. Just kind of sketch that tree out and then look at it. And it kind of gives you a more visual way to do it. I don't know. You do whatever works best for you, but I think the tree kind of has a nice look to it. All right, the disease problem. This sounds like fun, doesn't it? Maybe not. 1% of the population have a certain disease, and the remaining 99% are free from the disease. Okay, so makes sense. The 1% would have been enough. A test is used to detect this disease. The test is positive in 95% of the people that with the disease. So that's the conditional saying it's the probability that it's positive, tested positive, given that you actually have the disease. Okay. And then falsely positive is the ones that are free from the disease. So you probably hear stuff like that when you see something say, we'll talk about something being false positive or something like that. Yeah. All right. So if a person selected at random from the population tested positive, what's the probability that they have the disease? So what I was saying a minute ago, so like for example, this says it's tested positive given that they had the disease. Okay, what that tells me is that the branch of the trees need to start out with either disease or not disease. And then you go to the testing for the positive and negative. Now I use this lettering right here. I totally, like so you see just whatever lettering you want, but as long as you know what it means to you, in other words, how you define it. So I just went with D for having disease, and I just chose D prime. I could have used primes over here, but for some reason I decided not to. I can't tell you why I did that way. It didn't matter. But as long as I kind of clearly defined what I meant here, that's all that matters. But P means you tested positive for the disease, and N is tested negative for the disease. But yeah, I could have used P and P prime if I wanted to. So let's look at our tree, and then we'll focus on the question that it's actually asking. Disease, not disease. Okay, so 1% of the people actually have the disease. 99% of the people do not. So this second branch is after it's defective or not. So once again, this one I'll put the numbers in red that were given. So this number right here, then you go PN, whether or not you had the disease. So this 0.95 represents this number up here that says, okay, you have a 95% chance you tested positive if it's known you had the disease. So you see it comes positive given disease is 0.95. Okay, this one, we did not need these numbers, but once again, if it could have asked it, but sort of like I did when I went to that scratch page. So this obviously just has to be the difference that makes it add up to 100. So that's how you know whatever I wrote in red was given in the problem, whatever I wrote in any other color. Sometimes I just kind of want to always say purple, but it seems like I've been using purple. Not red will be sufficient. That just means I filled it in, even though we didn't really need it. This one says it tested positive 2% given that they did not have the disease. So 2% given not disease. So 2% testing positive given they actually did not have the disease. And then the 98 there makes it add up to 100. So let's see what the question's asking. If a person at random selected tested positive, what's the probability that he or she has a disease? So we're asking for what's the probability of it being the disease given that it tested positive. So it's going to be D given P. See, once again, it's not going to be P given D because we already have that number. You can pretty much guarantee it's not going to be that. So it's going to be the other way, D given P. So that's the whole purpose of doing this. They already gave us P given D. So it's probability of disease given that they were positive. So it's going to be so it's P of D times P of P given D. Maybe it's weird using the P here. I should use maybe something else because the P obviously outside means probability. Probability of positive given disease, and of course that starts out the denominator, and then this you have D prime that also leads to P. So it's everything that leads to the P. So on the top it's going to be 0.01 times 0.95. 0.01, 0.95, and then the bottom it's going to be the same 0.01 times 0.95 plus the D prime route, 0.99 times 0.02. And kind of work the numbers out, not too bad. You get 0.3242. So you got about a 32% chance that you actually have the disease given that you tested positive for it. Because note that we've already seen that the 95% tells you you're not guaranteed to have it even if you do test positive. So that's what's bringing that answer down. Then you have the route of the not having it route factored in there. So So it's not quite as high as usually the actual rate of having it is lower. Let's see. I think I may come back to this one. I just threw it in there if I needed time, maybe. Yeah, this one's kind of weird anyway. I don't totally like it. Maybe but I want to go to I guess my point is I want to go to my math lab mainly. I could always come back to this one. This one, the way they give the information is a little bit different. Actually, they kind of give all the three numbers you need right there. You don't have to do any. This one actually relates to the very first formula we saw, although it's worded kind of tricky, but I may come back to that one. But in the meantime, let me go sign in at Pearson here for a second. All right, so let's come over here and open up an assignment. Oh, I brought up, oh, crud, wrong, golly. Ugh. Wrong semester, wrong class, wrong everything. Swear I thought I clicked on the right. Well, I don't care about the day of the week. Doesn't matter. Whether I pick Monday class or Wednesday class, that's irrelevant because it's the same homework. I just completely picked the wrong false of I picked 2019 instead of 2020. So yeah, I just clicked on Monday. It's okay. Yeah, no, that wasn't the problem. Because you share the same homework. All right, let's see what we got here. Okay, Bayes' theorem. All right, well, let's just look at these real quick. And I tend to usually skip over these kind. Nothing wrong with them, but I like those that they start out like that in some of these sections. So it kind of gives you the sort of the practice of mechanically just using the formula itself, whatever. But I think you've seen just from what I've done so far, the skill lies from reading the wording of a problem. But I can always come back and do one of those. Oh, here's another disease one. Ha! I didn't realize that was there when I picked that other problem. I haven't even looked at or I think maybe I did at one point, but I just probably was in my subconscious. All right, well, these look good. Any of these look fine. Might do a couple of these. Business statistics textbook. I might come back and do that one, but I think either 3 or 4 look interesting to me. Company bidding on a shopping center. The banking problem looks interesting. I don't know. Let's see. I think I'll do this one if that's okay with you. So let me just kind of snip this problem out. One part, I guess that's probably got another. All right. Let's snip this out, and I'll go to my scratch page and work this out for you. All right. Okay, construction company A should have submitted a bid for a job, and its main competitor, company B, has submitted bids 70% of the time. Company B does not bid on the job. The probability the company A will get a job is 20%. If B bids on the job, the probability that A will get the job is 0.15. Okay. All right, so it looks like kind of a weird sort of looking path here. You know, I first looked at this problem. I'd assume, you know, when you see a company A and a company B, you think they're going to be the ones that are sort of side by side here on this tree. But that's not what we're looking at in this problem. It's like B, you know, the A is dependent upon B, in other words, what B does. So I'm thinking we're going to have, let's define B, company B bids on job. And A will be company A gets the job. All right, so I'm doing this one for the first time. Hopefully I won't mess this up. So if you think something, those other ones already worked out last night, so I knew those were okay. So by all means, if you think you see something you don't like here, chime in there. So I'm going to go like this path right here. I'm just do a B and a not B. Then I think we have an A and a not A. I need to, let me copy all this, or I didn't realize I was at the end of a page here. I guess, well, I can just drop the tree down, I guess, to the next page and leave everything else where it was. And we just scroll back up there when well, I can just bring this down so we kind of don't, so I don't scroll back as far. Yeah, I should have looked where I was on the page. I would have put this on a new page, obviously. I think that'll work. And then we need an A, not A here. With, you know, A prime meaning they did not get the job. Okay, so company B submits bids 70% of the time. There's your 0.7. Now we can come back and get that B prime, which I will. All right, I'm just going to keep everything in red ink right now, and I'll switch. But, you know, on a 2-branch tree, like I said, if you know one number, the second number means it has to add up to 1. So let's see what, if the company does not bid on the job, so we're going the B prime route, the probability that company A will get the job is 0.2. So the probability of A getting the job coming from B not bidding, that would be 0.2, would be right there. So obviously they've got to give me a number for that top part. If company B bids on the job, the probability that company A will get the job is 0.5. 0.15. This one, okay. No, it's fine. All right, okay. So I'll go ahead and fill the rest of this out in case we need any. We might need these, I don't know. But this we might not. But this would be a 0.3. This would be a 0.85. And this would be a 0.8 to make them all add up to 1. So I don't know if we'll even need those. So let me carefully read the question. If company A gets the job, what's the probability that company B did not bid? Did not bid. So that is going to look like this. P of B prime, let me just double check that, not bid given that A got the job. So once again, you see how these questions are always, the first one in terms of the second one? That's why they have to be used. You have to use the Bayes formula. Okay, so let's see what we got. We're going to have P of B prime times P of A given B prime. Now everything that leads to A on the bottom. P of, okay, same thing. Well, I can do B for, yeah, the order doesn't matter here on this. So I'll do the P of B just because it's at the top of my tree. But what I said earlier was, though, whatever you have in the numerator is always going to be one of the terms in the bottom. It didn't have to be first, but it will always be in there as one of the, in the mix. Yeah, so it's okay. I didn't have to put it first. So actually, I'll circle this to show you that we did have to calculating that number was important, but everything else we had. So we did have to figure that out, but that wasn't hard. So we did need a missing number there. All right, so let's see what we have here. B prime, 0.3. A given B prime is 0.2. And P of B is 0.7. And then probability of A given B is 0.15. And then I know that one on top is going to be there on the bottom. All right, so let's calculate this. I probably would try to avoid, I think I would try to do it one step if possible to avoid too much rounding in the denominator and stuff, because it mainly just for a test it wouldn't matter, but because you'd be close enough to the right answer, but you know how my math lab can be kind of picky at times. So 0.7 times 0.15. So I would try to do it all in one step just for accuracy. But that's okay. You probably, you might not need to do it, but let's just, this one you probably wouldn't, because it wouldn't have that many decimal places. But if you did do it separately, just make sure you use enough decimal places for what's on the bottom, because when it divides, that's going to affect it a little bit. So 36, 36, 36, 36. Now, what does it want? 3 decimal places. So 3636 would be 0.364. All right, here we go. Come on, give me a fantastic. Fantastic. Got it. I'm assuming you probably don't yell at these when you do it, right? So I don't know. What is the probability that just company A will get the job? That's kind of an odd question. Not a bad question. That's kind of an odd question, but I don't really see the point of asking that. But actually, that's the denominator. So I don't know why they're asking just for this. So this is the probability of A is all the stuff that leads to A on the bottom. So it's just the bottom part. That's why I don't see the point in asking that, but that's okay. I'll humor them here. So I'm just going to do the 0.7 times 0.15. I guess to me it would have made more sense if they would have asked this question first, and that's what's weird to me. And then if they would have asked what we just answered, that order would have made more sense. So I'm going to go 0.165, unless I'm not reading something right here. We'll find out, won't we? Bam! That was it. Okay, so I just thought that was kind of odd. Fantastic. I think I said that next one looked interesting to me, I believe, that last one. Yeah, let's see. Ooh, a lot of parts. That's not bad, though. That's actually good for us. We're doing really well. The next section won't take long either. So if I was worried about our time, you know, I might be concerned about doing one with so many parts here. But we'll do this one, and we'll have early break and come back and do the next section and probably have early finish. I know that probably breaks your heart. I could probably start talking about some other stuff if you really wanted to, but I know that we're going into, but I don't know. I don't have the notes totally ready yet, but I could know the material. So I don't know. We'll see. Let's see. This one's got a lot of parts to it, so we got time, so we might as well do it. All right, let's see. Now I definitely want to go down to a new page here. Let's see. I didn't even do anything on this page, did I? All right. Wow, we're up to 8 people, including me. Beautiful. Like I said, I didn't have any particular number in mind, but it wasn't going to surprise me if we had less than 10, just factoring in the circumstances of the exam and stuff. So, well, I'm happy that, you know, all of you made it. Let's see. In other words, I said I'm not upset at the ones that didn't. Oh, I better zoom in on this. I had to keep it small to get it up on the, but now I can't see it very well. All right, textbook company, blah, blah, blah. Business statistics textbook. Previous textbooks at 10% are huge successes, 20% are modest, 40%. Ooh, this is going to have a lot of branches here, isn't it? We're going to have a big old tree here. That's all right. We can handle it. We are that talented. Now let's read what the before books in 99% of the huge successes received favorable reviews. So 99% chance it was a favorable review given it came from the huge successes. So that just then tells me that the first part of this problem, which is probably not uncommon, is where it's going to start the branch of the trees. But don't assume that as a rule or whatever, but that's usually the case. Okay, I am going to save a little time here but you'll see what I'm doing, so it's not. I'm just going to use, so I don't list them out formally to save time. Huge successes, I'm calling it H. Modest successes, I'm calling it M. B for break even, L for losers. I just didn't feel like writing all those out. Sorry, I hope that doesn't bother you too much. I can feel your anger through the screen. Maybe not. HMBL. So we've got, you know, like this, HMBL. And those probabilities are 10, 20, 40, 30. So I'm going to put those in red. Like just my way of doing it, right? 10, 20, 40, 30. Yeah. Then what's the second branch involving here? Looks like favorable reviews or something that represents not favorable reviews. So I'm going to use F for favorable review, and then I'll just use F prime for not favorable, which we may not even need the F prime, but so I go F prime, F. I certainly don't think, well, I don't think, I'm certain that on an exam type problem, I don't necessarily want this many branches here. So it's just a little more tedious. It doesn't make it harder, but so it's just, let's see. So if it was a huge success, it was 99%, it was favorable, given that it was a huge success. 60% of the moderate successes had a favorable review, so we got 0.6 here. 40% of the break-evens were favorable. And then 20% of the losers favorable. I'm not going to worry about the rest of those branches of the tree unless one of the questions asks for it. Then I'll put them in there. But we know how to get those. That makes everything add up to 1. I'll tell you what I'm going to do here is I'm going to just cut and paste, a little snippy out this question here. I'll actually bring the question. I'm not getting rid of it where it is, just where I can see it below the tree here. All righty. The probability that a textbook received a favorable review, if it received a favorable review, I misspoke there. Well, all right. The probability it's going to be a huge success given that it was favorable. Oh, a lot of writing for this one. So it's going to be probability of H times probability of FH. And then everything on bottom. Okay, I'm not going to write this so neat. I'm just going to slap it in there. So the letters are H, M, B, L. And yeah, this would not be a fun test question. So that's just a little extra numerical work. I don't need those F primes, so I won't worry about them. So the F and the H. H is 0.1, so it's 0.1. 0.99. So that's going to be the first one. So it's just multiplying along those paths and adding each part. So 20 and 2.2 times 0.6. 0.4, 0.4. 0.3, 0.2. Yeah, so it just extends it, that base formula just extend it. Like I said, it can extend out to as many as it needs. Thankfully, obviously, that was the last problem in the homework, so it's not going to be any worse than 4. But so that's the whole idea of when I was putting those cases in the notes earlier, you saw that the last one was 3 or more, I think, whatever, yeah. You would just keep extending it as needed. All right, so we got 0.1 times 0.99 divided by, I'm going to get my parentheses started, obviously. 0.1 times 0.99. And 264432. 264432. All right. So I finally wised up and just quit saying that and just started saying it in my head instead of out loud, just as a little memory trick to myself there. But that would have got annoying if I just would have kept repeating that over and over. So I just started repeating it in my head. That's why I wasn't talking while I was doing that. So, 2255. Let's see what it wants. This number of decimals. Got to watch for that. I've even made that mistake plenty of times. 3. So 2255 I like as 226. Look at us. We are just too cool, aren't we? Let's snip this one over. Snip and copy that one over to that same scratch page. I'm having fun with this Bayes theorem. Wait, which? Oh, it's down here. Wait, where did I put that? Oh, it's on a separate note page. Okay. I have 2 open note things here. Probability of the book will be a modest success given failure. Failure. Favorable. Sorry. Favorable, not failure. Well, look at that. Probability of M given F. So I'm going to actually, well, no, I don't want to do that. I'm going to copy this because the denominator is going to be the same. So why reinvent the wheel here? In other words, that's everything leading to F on the bottom. So all we got to do is change the top. And the new top is going to be one of those ones on the bottom. Let's just see which one it is. Which one is the M and the F here? It's the second one, right? Oh, what do you want to bet it's going to ask all 4 of these? So actually, once you get this set up, it's going to be quick and easy, I think. 0.2, 0.6 now just becomes on top. Okay. So let me see if I can trick my calculator into, I don't have to trick it really, but I don't know if you ever used this feature before, but if you go second, enter, brings up your last command. So I can just scroll right back over to the beginning and go 0.2 times 0.6. Now for the 0.6, I can either put 60 or just delete the 9. I'll just put 60. That way everything. Oh, wait. Oh, that wasn't right. I didn't scroll over far enough. God, I completely messed that up. Oh, do I got to do all this again? What happened here? Why is it not going? I thought it's going back to all the other ones, but not the one. I know it stores a bunch of them in a row, but I don't know if it will get back to this one if I go. Golly, I don't want to make this mistake again. But it should have been simple. I didn't scroll back. I was changing the one right here inside the parentheses, and not the only one I should have been changing was on the numerator. Well, this stinks. I got to type all this in again. When I could have just gone second enter and I think it's 4. I believe it's 4. Let me check. 4432. Yeah. So I need to be extra careful on the next one. 2733, so if it wants 3, it'll be 273. All right, 273. Fantastic. So let's copy this one over. Yeah, unless something changes coming up here in one of these after this one, but yeah, it looks like we didn't even need the, it didn't hurt to draw the tree, like I said, for visual. I think it's a good idea, but I didn't have to complete the not favorable part of the tree. The F prime, I didn't have to even fill those out because it looks like it's not asking for any. Break even given F. So that's all these are doing now. They're just changing the numerator. So this becomes, so it looks like it's just moving one to the right each time, doesn't it? So without even looking, I'm going to assume that's the 0.4 and the 0.4. Because I followed the same order, there wasn't a problem. We'll double check though. Yeah, 0.4, 0.4. All right, now let me be extra careful here. I'm going to go second, enter. And this time I'm going to go make sure I see it's got that left arrow over there, meaning there's more stuff there. I didn't go back to the top. There we go. See, that's what I didn't do last time. Now if I go 0.4, 0.4, now we got it just by making that one change. 0.364. So the last one's under 0.5, so I'll go 364. Fantastic. And then, okay, kind of what we expected, the way the pattern was going here. But I think this one has a lot of potential. I guess one nice thing about seeing this is, you know, even if that way it's just to say you don't stop for a while till you go back and work this problem. If you can just remember, oh yeah, he did that one in the video, so I can go back and watch if you just remember that I did it, you know, you could go back and then look. Even if you don't remember how to do it, you could say, oh yeah, he worked that one out. In fact, if anybody asks me about this problem, I'm going to say, hey, watch me work it out in detail. I'll say, look at the video at about the, what is it, the 1 hour? I don't know if I'll remember the 1 hour and 15 minute mark here, but I'll just tell them it's going to be at the end of the Bayes theorem part because this is it for this. We go break and then we move on to the last part. Next section, we're going to learn how to count. So get your fingers and toes ready and start counting. Not quite that kind of counting. Okay, so did I use L for loser? I assume I did. L for loser. And then we just change this to the last one, the 0.3, 0.2, same denominator. So like I said, it's looked like, yeah, okay, so there's a lot of parts and a big tree thing, but it made it kind of easy to, you know, get each, once you got the first one worked out, you know, using the same denominator. And so it wasn't, so I'm going to go second, enter, and I'm going to be careful this time, like I was the last time, but not the first time. Point 3, 0.2. 0.137. So let's see what we got here. Well done, hooray. Oh, I got excited. There's another part here. What proportion of textbooks receive favorable reviews? Just like that other problem, it's now asking for that denominator only. Because that denominator is, let's see if I can, okay, I can just go second enter and just get rid of the first part of it. Yeah, so it seems to want to ask that on these questions, so, all right. So I'm going to delete it. Get rid of the division, and we don't have no division now, so it's just that part only. 0.439. Yeah, I'm glad I didn't do that other problem in my notes. I'll probably just go ahead and delete it, or I mean, if I could leave it there if somebody wanted to try it. But yeah, that one I added because I didn't realize when I wanted to do these, and then of course, because you never know how many parts these things are going to have. Hey, nice work. So, okay, it's break time now. So let's see. I don't know, 6:47 is 7 o'clock okay, or is that too long, or what do you think?
No,
that's fine.
Is that okay?
Yes, sir.
All right, so let's
Yes,
I'll bring up the next thing on the screen here, and just to have it up here, and counting rules. So I'm going to walk away from the computer a little bit here, and you'll hear me start talking again right at about 7 o'clock. So how's that going to be all right? All right, so. All righty, welcome back for round 2. I'll check the chat here real quick before we start. So, okay, that way it's been a good time to see if there's anything written in there I need to respond to, and looks like nothing's there. So let the games begin for round 2. I promise you we're going to learn how to count, but, you know, a little more advanced than normal counting. Now this book, I guess we're not going into I looked at it as not going into because usually, you know, when I teach that finite math course, and you probably saw it too, we learn these rules and then they apply probability questions, you know, based on these rules, but I didn't think so. So we're moving on from after that. We'll just learn how to do these counting things. So that's fine. Now let's see. This says that, what is any one of K different mutually exclusive events and collectively exhaustive events, which I did not define before. I'm thinking about going back and adding that into, even though I won't test you on it directly, but I think I'm going to repost the notes from 4.1 and add that terminology in there. It really hasn't affected us, really, so I haven't worried too much about it. And it won't affect us here. But it does keep popping up from time to time. I've never seen other books use it, and not to the extent that this one is. Usually they just use the mutually exclusive and consider that good enough. But anyway, we're not going to worry about it. Let's see. All right, so if you it's basically the same outcome over and over and over. If you the number of possible outcomes that you can get within n trials would just be k to the n power. Like this one says, if you flip a two-sided coin, the total number of outcomes. You know, if you ask people this this already has the answer there. So if you say, okay, you got a coin flip, has two outcomes, heads and tails, you flip it 5 times, how many different 5 orderings could you get? You know, those 5, and sometimes they'll go 10, you know, 2 times 5. Actually, it's not 2 times 5, it's 2 raised to the 5, because you get heads or tails each time. Head, tail, 32. So, I mean, you know, you don't need to back this up, but if you know, I wouldn't do it for 32, but you could check it for 8 real easily. If you did like 3 coins, it'd be 2 to the 3rd, which is 8. But when we say 32, we mean like this would be, all right, H, well, that's 1, you know, and H, T, and then all the different orderings, there would be 32 of them total. That's what we mean by the number of ways a 5 coin outcome can end up. So, all right. Yeah, you don't want to list all those out. That'd be kind of, well, if somebody was going to list this out, actually the best way to do it would be using a tree. I wouldn't call it a probability tree, but you just sort of go HT. If somebody had to do this, and you don't have to do this, but so forth. I'm stopping at 3 here. And then to list them, so there's definitely 8 outcomes. And you'd follow along the branches of the tree. Ooh, I accidentally hit the eraser there. H would be 1. HHT, HTH, so forth and so on. Yeah, I've seen people try to do that sometimes in their head, and I know there's 8, but I'm only getting 7 of them. Which one am I missing? So that's why if you try to do it, you can do it by thinking through it, obviously, but well, 32 would be really difficult. All right, how many 5-digit zip codes are possible if each number may be repeated? So that's when we're going to talk about other stuff that involves repeating and not repeating. But obviously this is important, because if this can be, you know, that affects the answer. Now 0 through 9, that's 10 digits. You count, I mean, you might think, is that only 9? But no, because 0 counts as 1, so that makes it 10. So it's 10 digits. So you would just say 10 for the first one, 10 on the second one, 10 on the third, 10 on the fourth, 10 on the fifth, multiply them. These kind of questions, sometimes you can see them for like lot combinations. You know, so if you had a 4-digit lot combination with 10 on each one, and any one of them is possible, there would just be 4 10s multiplied together. So there'd be 10,000 different possible 4-digit combinations if every digit is allowed to be used. Like I said, we'll talk about situations where maybe that's not true later, but okay. So now this says how many 5-letter codes are possible, but only from the first 7 letters of the alphabet. So that's important. If it would have said the entire alphabet, this would have been 26. But the first 5 letters, so it'd be 7, 7, 7, 7, multiplying 16, 8, 0, 7. How about that? So far, so fun, so good. There's 5 of these counting rules. Of course, we'll do some my math lab stuff on it. I suspect this is not going to take as long as the first half, maybe per se. But, you know. Let's see. Now, here's another counting rule. Now, this could be where it's a general of the first one, but it can allow different item. It's not the same item repeated over and over and over. It's more of a general version where you can have different things, and you're choosing one of each particular item out of the group here. So, and you still multiply them though. This says deli serves meat sandwiches with three kinds of bread, 5 kinds of meat, lettuce or sprouts. How many sandwiches are possible assuming only one item is used out of each category? And it would be 3 times 5 times the 2. The 2 doesn't show you the number 2, but lettuce and sprouts together mean they're 2 choices. So it's 3 times 5 and 2 is 30. One example I like to use, I forgot to put it in here, so I can always go to my note thing here. Try to make sure I do this one live on Monday also. I use this one, and I just forgot to put it in there. I may go back and add it, but I may not. I don't know. Okay, I always talk about, suppose a woman's dressing up for a fancy evening here, you know, and sometimes if I'm doing a face-to-face class, I'll let the women help me with the numbers and whatnot here, but just to, you know, so you don't have to worry about that in this environment, I'll just make them up. Or if you see something blatantly wrong here, you know, you can correct me. I do know that shoes needs to be the number 1 choice here as far as the most items. I don't know anything about shoes. So we're going to say, I don't know, we got 30 pairs of shoes, 15 dresses. I don't know. What was I using? I'm not using undergarments, but shoes, dresses. Was I using gloves or something like that? Or I forgot what I was using, but or hats. I don't know. 5 hats. And purses. Yeah. And let's say that there were 10 different purses that you own. You might not wear the hat. Choose one of each. How many ensembles there are possible? Now this is taking one giant factor into play here that's probably not reality, but for this exercise it kind of needs to be. We have to assume that everything coordinates and works with each other to make this math problem. You know, I mean, everything has to match here. So I know that's not the real world, but it has to for this. So you're wearing one of each. So how many different combinations could you have? 30. I mean, I literally know nothing about fashion. So, but let's see. So what is that? Let's see. 45, 225. I got 22. There'd be 2250 if I did that right. Number of choices. Like I said, but that's taking a lot of things into assumption here. What if everything was black? Would that mean it would all coordinate with each other? Basic black? I don't know. But I guess the problem is like purses, some are fancier than others, I guess, you know, so it's not so much even the color, I guess, as probably the style. I better shut up. I don't know what I'm talking about, but anyway, just the math of it, that's what you do. You would just multiply those 4 numbers together. Thank goodness the math part's easier than the fashion part. So, all righty. There's probably some men out there thinking, yeah, and I've been waiting around while she tries on every combination. Just kidding, you know. I felt like they waited while everyone was being tried on. Oh, here's a chat comment here. I'm probably going to get yelled at here. Let's see. Fashion way easier. Yeah. You know, so obviously that's kind of a silly problem, but I think the important thing is I think you see the idea behind it and the number. I mean, if you don't, let me know, but I mean, you see you know, it's just a matter of multiplying those 4 numbers together. Here we go. Now we'll look at with and without repeats. Now some I would say with repeats because obviously, you know, you can choose. Obviously, some things repeats would make no sense, like flipping a coin. You know, of course, it's going to repeat. I mean, not having a repeat would be silly. But this one, in other words, you can reduce. So like this one is saying, so with repeats, if you have a license plate with 3 letters followed by 3 numbers, how many combinations are possible. We'll do with and then without repeats. So with repeats, you'd have the 3 letters would be 26, 26, 26, and then 10, 10, 10. For 17,576,000 people, or comp possible combinations. But look what happens if you throw in the statement of without repeats. So if you use a letter, that letter is gone. So you have 26 on the first one. Whatever letter is used there is gone. So it goes to 25. And then both the first 2 letters are gone because they can't repeat. Goes to 24. Then you start fresh with the numbers at 10. That first number is gone, so you're down to 9. Then the first 2 numbers are gone, and you're down to 8. So there's how the phrasing of without repeats would be calculated. You just drop in 1 each time, so forth, and you end up with 11 million or something like that. So, ooh, now this one's challenging. Oh, I put it. I decided to squeeze this in there instead of moving it back where it was. So I did a zip code. If you're saying zip code, if it can't be repeated, 10, 9, 8, 7, 6. You're losing 1 each time or whatever. So let's go back and look at this one. This one's kind of challenging. It's about as tricky as we're going to make these kind of problems. It should be pretty straightforward other than that. But this one's a little interesting. It's a letter followed by 4 digits, but it's got some rules assigned to it that are more involved than just, repeating or not repeating. So any letter can be used. The first digit cannot be 0, and the last digit must be even. So how many combinations are possible? First letter, it can be any letter, so all 26. Now the first digit cannot be a 0, which means it can be anything 1 through 9, which gives you 9 choices right here. And then for the third and fourth, there were no restrictions given here, so all 10 is possible. But the last one has to be even. Now don't count zeros. 0 is not an even number. 0 is just kind of 0. So the even numbers then would be 2, 4, 6, and 8. So that's where the 4 is coming from, anywhere from 2, 4, 6, and 8. So there's 4 choices here. Then you multiply those 4 numbers together to get this result, 93,600. How about that? Was that fun? That was fun, wasn't it? Now we're kind of getting an idea of arranging things in order, where the order you put them in will matter. This little exclamation mark in math, and I'll show you this in the calculator in just a second, so don't worry. Well, other calculators probably, if it's a scientific calculator, it's probably got factorial on there somewhere. Now, on your less expensive scientific calculators, it's probably on the keyboard, but the TI 8384 family, all that has so many functions. There's only so much it puts on the keyboard, so you have to go looking for it. But if you're not sure, take whatever your calculator model is and say, hey, where's the factorial? And Google it up. Where's the factorial on the blah 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 calculator? And I'm sure you can find something that tells you. Sometimes they use X instead of N. You might see something that says X factorial, which is fine. We call this N factorial, where N factorial means it's the number N times N minus 1 all the way down till you get to 1. And by definition, 0 factorial is defined as 1. It can't be 0, so it has to be 1. So another way to look at it, it's one way. You can choose nothing is another way to look at it. But so, in how many ways can 5 paintings be arranged on the wall? It'd be 5 times 4 times 3 times 2 times 1, which is just 5 factorial. If you know it's 5 factorial, you don't have to write all those numbers out, but I was just showing you. So basically what it's saying is there's 5 ways you can pick for the first painting. Once it's picked, it's gone. Then it goes down to 4, and then it's gone. 3 to 2 and 1, 5 factorial. So like I said, this stuff only applies to non-repeating items. It's got to be something that, you know, goes away once it's used. So 5, 4, 3, 2, 1, 5, and I'll do the calculator after we do the next one. Let's see. How many ways could a batting lineup of 9 players on a baseball team be arranged? It'd be 9 factorial. And if you're just allowing anybody to bat in any order, that's a pretty good size number right there, isn't it? 362, 880. So let me show you this in the calculator now. And this is a newer version, but even the same idea on the older TI-83s. It worked just fine. It'll be the same idea. So actually what you got to do is you got to put the number first. So it's 5, and you go to math. I think there's one extra thing here versus the old TI-83s. Only that one may not have the complex one there or whatever, but it doesn't really matter. PRB, and then you scroll down to number 4. All right, let's see. Factorial right there, number 4. Hit enter. There it is. So we got 9. Yeah, these factorials can get really, really large in a hurry. I mean in a big hurry. So let's just kind of, I won't write this down, I'll just say it verbally, but let's say you took, I was in a real classroom, and there were, say, 20 students. 20. It's different if you don't have the same number of seats as you do students, and we're not worrying about that. But right now, it's just say there's 20 seats and 20 students. How many different orders could 20 students sit in 20 seats? How many different possibilities are there? So it would be 20 factorial. This at the end means times 10 to the 18th power. That means you would move this decimal place over 18 times to the right. So once you got past that 8, you would add a bunch of I don't know, it's not even a number I can say. It's well beyond trillions, you know. It's what I'm something, you know, I don't, there's not a name for it, you know, whatever, but it's astronomical. And it just seems, but it's, you know, it's mathematically solid, but it just, I think that kind of seems bizarre to people, and I can see why. Go, how could 20 people in 20 seats generate a number of combinations that's a number that's gigantic like that? But it is, it's true. It's mind-boggling, isn't it? I mean, it's just like, holy cow, 20 people in 20 seats is this mess? Yeah, it's pretty scary. That would be a pretty rude game of musical chairs. Let's see. Continuing the idea of order. Now we're going to be looking where it's not necessarily just one particular, it could be choosing out of a certain number of things to get them in order. So we're taking, in other words, a subset out of a larger group and putting them in order. We call that a permutation, is the name of it. Now I'm going to show you the calculator function, but this is the actual mathematical formula for those that are just using, I see a lot of calculators, these basic scientific ones, sometimes will have these combination and permutation formulas in there, but if they don't, you just have to use the factorial formula. You'll be all right. I got confidence in you. Let's see. I saw something flashing there. I thought it was about to time out on the My Math Lab. I don't want it to time out. I will exit this though. We are going to go to 4.5 here in a minute. I'll go ahead and just open it right now. I thought it was going to go into shut off there. So you can use, as long as you have the factorial, you should have the factorial key at a minimum, but you can use, so it would be n factorial over n minus x factorial, where n is, so you're arranging x objects selected from n objects. So your n is the grand total, x is the subset number that we want to choose here. So P is just for the word, permutation. All righty, so let's jump in here with this real quick. Yeah, like this. So we're choosing out of a group. In a horse race, how many different finishes among the first 3 places are possible if 10 horses are running? We'll talk about, that's going to be the key difference between this rule and then the next rule, where the order will not matter. But here, the order is going to clearly matter of which horse finishes in which position. So this kind of problem, anything involves any kind of horse race, human race, automobile race, anything like that, it would certainly be a permutation. The order would matter. Because let's say, you decide this weekend you're going to go over to the horse track, have a little fun over there at Sam Houston, and you go up and bet on what's called a trifecta, which is predicting the first 3 horses. So let's say, you wager that it's going to be 2, 1, and 6 because you're betting on that order. Well, if it finishes 1, 6, 2. You had the right 3 horses, but you're not going to win because you did not have the right 3 horses in the right order. So it's not like you're betting on which 3 you're going to finish in those positions in any order. There is no bet like that. Well, unless you do, you can pay what's called to box them, meaning you're including all 6. There's 6 combinations for 3 of them. So if you covered all of them, that's different. But I'm just talking about if you only bet on 2, 1, 6 in that order, and it finishes 1, 6, 2, you do not win. So that kind of idea implies order for sure, any kind of race. So using the formula, it would just be 10 factorial, and where am I getting 7 factorial from? I forgot to write that out, but it's 10 minus 3. That's where the bottom's coming from, is 10 minus 3. So if you do it, and you can do it, I'll show you, then I'm going to show you the permutation formula here in a second. But I'll do it with factorials. And I'll do the 10 minus 3 just to show you. But I did forget to put it in the notes there. Sorry. Okay. But I'll put 10 minus 3, and now you can actually see where the 7 came from. All right. I mean, obviously, I don't think you would do it this way if you were working it out, but I just wanted you to visually see that. 720. All right, now I'm going to show you how to do the permutation in the calculator. Now to do this, and I mentioned this, and it's in the notes too, and I know sometimes the notes don't make it totally clear, but I'll show you down here. Now, that's why I wrote this step. I'm about to say it, do it, show you verbally, show you, but you have to enter the first number before you use the function. So watch what I do here. Before I even choose the permutation formula, I have to put the 10 in there first, like that. Now I go the same place I was, math. I think the older calculators just use PRB instead of probability. I want that number 2, and PR. P is for permutation, and C is going to be combination, which is what we're going to learn with counting rule number 5. All right. Enter. Then you hit the second number, which is 3. Because even though the formula was 10 factorial divided by 7 factorial, it still meant choosing 3 out of 10. So you enter 3 as the second number. I hit enter. Well, either I got really, really lucky or I did it right. I think that I did it right. So there we go. Isn't that fun? I'm just always assuming that you're saying yes. You don't have to say anything. So I just assume it means yes. Okay, foot race, people race. 5 people out of 50. Of course, excluding ties. Boy, this is going to be a whopper of a number here, isn't it? But it's 50 divided by 50 minus 5 factorials. That's where the 45 is coming in. But hey, we can just go to straight to the calculator. These numbers can get kind of rude. Imagine if you did this for like a marathon. Oh, I don't even want to know. Like how many different first 5 finishes can you get out of a marathon? I don't know how many people even run those things. 1,000? Is it more than 1,000? Probably blow up. The calculator can only handle stuff that goes from to 10 to the 99th power, so it'll give you like an error if it's too big. I might try it just to see if it's too big for this one. I think, in other words, I think if 69 factorial is the largest factorial you can put in there, 69 or and then 70 blows it up and says overflow error because it's beyond times 10 to the 99th power and it can't do it. You heard its little brains. So 50, choose 5. 50, math, NPR, there's that number. Only 254, over 254 million ways you can get the order of 5 out of 50. I still want to know how many run a marathon. That bugs me. I mean, obviously it's different every time, whatever, but is it really 1,000? Is that many? Maybe I'll just do 500. How about let's do that? Top 5 out of 500. This might blow the calculator's brains out here. It may give me the finger here. But I just want to see. I'm curious. Oh, wasn't that bad? Okay. But still, that's a gigantic number. Because you have to keep moving it to the right. So there's 13. So there's 9 decimals. And you'd move it over and you'd move the whole thing over. So it'd be then 4 more zeros at the end of that. So big old numbers. Now, let's see. How many ways can a president, vice president, and secretary, you're going to form a subcommittee out of 7 people, and you're going to form a little subcommittee that consists of a president, vice president, secretary. Let's see. Well, let's talk about that. Think about that. Was that something we think that the order that we choose them, would that actually matter in this case? And we're going to look at a case, where it doesn't matter here, and then we go to the next rule, but next counting rule. But yes, that would make a difference. Because they're ranked by different positions, right? So you're choosing them for president, and then you're choosing a vice president, secretary. So in this case, order would matter, and I wouldn't just preview it for you. But if it had just said we're just choosing a subcommittee of 3 people out of 7 people with no specifications like it has here, then the order would not have mattered, and we would use the next formula. We're choosing, if you're just choosing 3. Here's another example. So, obviously I'm not going to do this for reality, obviously, but let's say, okay, I'm going to choose 3 random people out of this class. One of you is going to get an automatic A in the class. One of you get an automatic B. The other one gets an automatic C. Well, dang, the order would certainly make a difference in how you chose that, wouldn't you? But then what if I phrase it as, all right, I'm going to choose 3 people at random, and all 3 of those students are going to receive an A for this course. Then it would make no difference what order you were in then, right? Because it wouldn't make any difference. You get the A no matter what. So, okay. So that's because it's distinctive positions gives it an order meaning to it there. So it's a permutation. So it's not a hard problem, but there it is. So 7, choose, oh, wrong. What, I can remember to repost these notes. Wrong, 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 wrong. 7, choose 3 is right, but that makes that 4 factorial on the bottom. Ooh, uh-oh. I did it right numerically because I put it in the calculator, but that's 4 factorial. Bad, teacher. Yeah, let me just rewrite this. Let me just rewrite this now. Yeah, thankfully everything's answered correctly here, but boy, if I had not caught that and kept going, I bet you I would have got people that, you know, went back and watched this later would have. Nothing more frustrating than when you think you understand something and then actually the instructor error made the mistake, not you, you know. Probably thinking, man, just when I was starting to understand this, and oh, it was my fault. I don't like that 0. It looks too much like a O. It bugs me. A little narrower, that's better. Ah, sorry about that. But you see, it was correct to put it as 3 in the calculator. But the calculation's leading to 4. All righty. Thank goodness we got the, I noticed that because that would have been frustrating had I not. There we go. Yeah, this this book doesn't even go into, like, you know, I know when I do finite math, it goes into where you have to sometimes multiply 2 of these together from 2 different groups and stuff like that. But I'm just doing whatever they put in there. It's fine. So I wish they would have done that, but that's okay. They've kept it actually simple, so I guess that's all right. Because you could, you know, you can have one where things that are coming from 2 different groups. Like, say if you had this one would be where the order didn't matter, you know, where, okay, this first group, you know, however many people you're choosing, I don't know, 3 men and 4 women out of 10 people, and then the next group you're choosing 5 men and 4 women out of 12 people. How many total choices are there? So you would do them separate, then just multiply the answers together. So, all right, anyway. So this is basically, it says irrespective of order, and order does not matter. In other words, I put this little clip from another book in here or whatever. So the main thing is permutation. The order vital, order matters. In a combination, the order is irrelevant. So it doesn't matter, you know, position-wise or anything like that. So if you're actually using the formula, if you need to use the formula, it's similar to the permutation formula, but it just has an extra x factorial there in the bottom you have to deal with there. So, because it's a different calculation, therefore it's going to have different answers. So obviously the formula needs to be at least a little bit different, right? So, but like I said, you're going to see how, if you're using TI, you're going to see how to do it in there. And I've never looked it up, but I'm sure if you Google it and look it up, Excel probably does permutation and combinations. I don't know what the command is, but I mean, I might just pop the screen up for a second without, I don't want to now switch over and start doing these in Excel, but I'm going to see if I can do, if I just pick an open cell here, if I go equals, you know, start spelling out permutation, equals P, E, R, M. Oh, you see something with permutation A. Why does it have? I don't know. I'll just put 2 numbers in there and see what happens. But, you know, you can, like I said, you can look this up if you need to. That okay. So whatever I'm doing wrong there, but it looks like it can handle it. But anyway, whatever. But I just don't waste any time on that more. But obviously, if you have the calculator, that's by far the beautiful way to do it. All right, so here we go. Now this is a committee choosing thing, and now it's not the same numbers as that other problem, which is fine. But this is good because now it's not specifying that the 4 people you're chosen are going to be, you know, one of them's not going to be the lead, you know, the president, vice president. There's no ranking associated with it. You know, it could be like you're just choosing, okay, we're going to draw names out of a hat for, you know, free trip to Hawaii or something like that. So we're just going to choose any 4 out of 12. So 4 people chosen at 12. It's a combination because the order is not going to matter. And the formula would be 12 factorial on top, 4 factorial on bottom, and then 12 minus 4 factorial in the parentheses. So you see it's got that one little extra part on bottom. That's important in case you're just using a calculator with the factorial key on it, you know, and you're having to type it in. Let's see. Now let me, I can enter, I won't retype this one in. I'll just kind of zoom in on it so you can see it here a little better, but I'll do the combination. But there's sort of the manual way. But notice something very important here that doesn't apply to permutation because permutation only has one thing in the bottom. But look at this. This, notice, very important, like I was doing earlier with those Bayes problems. You know, anytime that you've got several things in a denominator, you know, you need to wrap parentheses around it so that the calculator knows you want all that contained at the bottom. Because if that parentheses is not there, I'll tell you, I can type it in there and show you the answer would not be the same. If the parentheses is not there, I'll tell you what, I'll do that. 12 factorial. The calculator is going to think, well, let me just type it first before I hit enter. Divided by 4 factorial. And then I want to put times 8 factorial. This is not going to be right because I'm trying to illustrate a point. Because let me tell you what the calculator thinks that means. That calculator thinks that means 8 factorials in the numerator. It thinks it means you want to then multiply after the first step times the 8 factorial. The parentheses keeps both of them together in the bottom. Or you could actually go divide. That works. But parentheses works. This is going to be a big old number. Yeah. So either parentheses, yeah, I forgot to mention that. Or, like I said, if I change this to divide works. Yeah, there's that 495 answer we're supposed to get. So let me do the combination thing real quick. It's real easy. Once you know how to do permutation, just pick the right one. Use the same command, same area. The factorial and these two things are all right together. There's NCR, number 3, right below NPR, right above the factorial. So you go 12 NCR, 4. There we go. So yeah, the calculator is nice that, you know, for the commands it does, like entering that factorial, but you know, you still have to be the brains behind it when it comes to things like order of operations. You know, it doesn't, it can only, the calculator is only going to do the order of operations. It's not, you have to make sure you know, you set it up the way you want it to be done. So that's why, you know, we needed parentheses because that's the number 1 on the, please excuse my dear Aunt Selma or whatever that is. You know, you want this to be done first, so you got to wrap parentheses around it. All right, here's one. Let's say you take a standard 52 card deck. How many 5 card total hands are there? I'm not going to retype this one just to save time. Let's just take a look at what's in the box over there. Because we're going to be doing a My Math Lab homework problem anyway, so you'll see me enter it again. So I did it with the formula. I used parentheses. Got a 5 factorial and a 52 minus 5 factorial. And then I got that 2598960. And then it did 52C5, 2598960. And that's without even counting order. Doesn't even matter. Imagine if order mattered here. Holy cow. So let's say you had a hand that was the 2, 4, 6, 8, and 10 of diamonds or something like that. It just counts it once. It doesn't matter, you know, there's not counting the order. It doesn't matter, any order counts once. Yeah, now I'm kind of curious what this number is going to be. If it did matter, this ought to be a whopper here. No, in PR, if that mattered. Yeah, card things are generally not order related. Yeah, look at 311 million versus 2 million, almost 312 million versus 2.6 million. Quite a bit more if the order matters. All right, a shipment of 30 calculators is being shipped to high school. 4 of these calculators are designated for Mr. Fred's calculus class. How many selections can be made? Just, you know, randomly pulling out 4 calculators, how many different ways can you pull those 4 calculators out? So it's just 30 choose 4. So you see so it's 30 divided by 4 times 26 factorial, each of the factorials multiplied together, or the quick and easy way, 30 choose 4. And that kind of covers the content part. So let me just jump over here and let's play around with a couple of homework problems, and then we're done for this week. Let me move forward a little bit. I'll kind of skip over the easier ones. This one's easy, but we'll go ahead and do it real quick. I'm not going to copy and paste this one because it's not that much work to it, actually. Particular brands of women's jeans is available in 6 sizes, 2 different colors, 4 different styles. How many different jeans does the store manager need to have 1 pair of each type? 6, 2, 4. All we have to do is multiply 6 times 2 times 4. Well, I'm going to get all fancy here and do this in my head. I don't mean to scare you. I come up with 48. We are awesome, aren't we? Look at us. So that's some fun math right there, isn't it? So let's move on. But obviously I want to get the combinations and permutate. There's another one where difference. You know, how many blah blah blah. You can make so many burgers. Okay, that's kind of the same thing. 13 teams of a high school basketball league. How many different orders of finish are possible for the first 4 positions? So do you agree that order would matter here? It would matter, wouldn't it? So it's going to be a permutation. 13. Choose 4. I'm going to go with 17160. I think it's going to be a good job this time. Good job. Excellent. Okay. I'll have to guess them just for fun. Okay. So order mattered there. Let's just hop around here and $13 rows, 13 different vegetables. That should just be 13 factorial. I'm just going to make sure I jump, yeah, most of these are pretty, sometimes they tend to get more complicated toward the end. But actually, if you did the one that was the Gardner 13 deal, you could do a permutation, because actually, P1313 would end up being just 13 factorial. So yeah, you don't have to be listed as a permutation, but it would be one. All righty. How many different ways can a senior project manager and associate project manager be selected for an analytics project if 12 data scientists are available? I got to think order matters here. What are you right? Because they're two different named positions. This is very similar to the president, vice president problem I did earlier. Secretary, whatever it was. Yeah, so I'm going to think there's 12 total scientists, and we're choosing 2 where the order matters. Well, this homework section has a lot of potential, doesn't it? I mean, once you kind of have a grasp of what's going on, you might be able to fly right through this one. It's funny because it's got more problems than most of them, but I can see why now. Because it's just, and they're not multiple parts. You just boom, 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 132. Well done. Look at us go. Man, we are awesome. So let's knock out a couple, 3 more of these, and that's what we're going to call today. 17 members of a group, a team. How many ways are these 17 members? I didn't do that other one with the gardening one, so I'll do this one. So 17. Oh, wait a minute. Let me think of this one. Order's not going to matter on this one. Let me think about this. How many ways are to select the kind of tricky because I can't tell. Because, if you're being selected to be on the team, it's not saying, it doesn't imply order here. I don't think. We'll find out. I'm glad we did this one. Well, I'm going to show you why I knew this answer was what it is. If it's right, if it's wrong. If I'm right, 1's the right answer. No. 17, choose 17 should be 1. But it's indicating it is combinations. So, all right. Oh, was it 7? Oh, at a group of 20. I didn't even, okay, I'm sorry. I thought it was 17 out of 17. See, I can't even read the question right. Okay, it's 20 choose 17. But I was right about the order not mattering. Good Lord, okay. Man, now I see why students, I'll tell you here in a minute. I don't know how I just missed this. So now I'm going to go with 1140. Okay. But I was going to say, now I see why students get frustrated sometimes. Like I'll have problems and examples and notes, and they'll, especially like in a face-to-face class, so they'll tease me sometime, whatever they go. I see why I go, I hate it whenever numbers are expressed as words. And it's funny because that 20 slipped right past me. I didn't even notice it. So I see what their point of view now or whatever. So, if that would have just lit up gigantic if I would have seen the number 20 there or whatever, but so now I kind of see what when they're kind of messing with me, what they're talking about there, so I got fooled.
I got a quick question on that problem. So
Yeah.
I could have started with 17 and then go into the probability and selected NCR and then type 20.
20 NCR 17.
Or do the opposite, how you had entered 20. What about if I would have entered 17 and then?
What?
Does the order matter?
What
Does the order?
The order matters on the numbers you enter. I mean, yeah.
Okay.
The smaller number can never go first.
Okay.
Here's why I thought it was 1 before, because I knew that this answer was going to be 1. I thought it was 17, choose 17. And I know in a combination, just from my experience, I know that that's 1. So this is how I got 1 originally, was because I did this. I completely missed that 20. I didn't see it. That's how I knew this was 1, but even though it was wrong, but because if the order doesn't matter, there's only one way you could choose, so, there's not more than one way if you're not specifying order. So is that okay?
Yes.
Okay. But when I talk about, okay, there's 2 ways to say order. Order, the larger number goes first, but when we're talking about ordering of the items is what I mean. Ordering of the items, that's when it's permutation versus combination if the ordering of the items does not matter. Ordering of the numbers, the largest or the smaller number, it can be the same number sometimes, but you can never have when you enter them in the calculators, can't go smaller. I'm sure it's going to give you some sort of error or something. It's not going to calculate anything. I'll check and see, but it's definitely not. So in other words, I don't think it's going to give you the wrong answer. I think it's just going to give you yeah, I've never done it to see what it does when it does this. It's got to give an error. Or 0, okay. Or it just gives you 0, which is not the right answer either. I thought it would give an error, but it didn't give the right answer, though, that's for sure. I thought it might be programmed to say, can't have the bigger number second. All right, so let's see what, okay, I misread that 20. I'm going to go back and look at it now real quick. Let's see what it is now. That's still 20. I thought it might have changed the number. I guess I won't change the numbers if I've already gotten it right, I guess, right? So, so there's a combination. We might try another one. Student has 9 books. Oh.
I'm sorry. I was going to say on the last problem, if you clicked on that familiar problem, it would have gave you different numbers.
Oh, the similar thing here, right? So yeah. Oh, I see. You have more experience of doing these than I do, obviously. So yeah, that's what it is. That's what, right. There you go. So 6 members of a group of 9. So that'll be 9 choose 6. Okay. Very good.
Professor?
Yes.
Can you show me number 8?
Huh?
Number 8.
What about it?
Can you show me?
Can I finish this first?
Yeah, sure. Go ahead.
Was that one I've already done or haven't, or did do or didn't do, or?
Yeah, I think you already did number 8. Yeah, I just wanted to see how you did it.
It was 12 choose 2.
Okay, thank you.
Permutation. Can you see the top number on the screen there in the calculator?
Yes, I do.
Yeah, it's permutation. That's the key, is it's permutation. So keep that in mind. Sometimes if you're doing a problem and you're pretty sure you have the right numbers, they're like 12 and 2, and you're not getting the right answer, it could be because you didn't choose, you choose permutation, should have chosen the other combination or vice versa or whatever. So, but that one was permutation because it was the order between the 2 positions mattered. Senior project manager and associate project manager. So that made a difference in the ordering versus just saying selecting 2 data scientists at random out of 12. That would have only been the combination.
Okay, thank you.
You're welcome. 6 members of 9. So we already did that. Okay. Let's see. Student has 9 books to place in her backpack. There's only room for 6 books. Regardless of the arrangement, that's just a fancy way of telling you order doesn't matter. How many ways are there placing of 6 books in her backpack? So if they would have said something to indicate that they needed to be in a certain order or something like that. So there's nothing indicating this is an order, so it should just be 9 choose 6. Let's see if that's right. Yeah, I'm just saving time by not actually, if you're using a formula, I'm sorry. You can stop me afterwards. I'll be done here in a minute. And then if you're doing it and you need me to see me write the formula out, but just to kind of do more problems and kind of speed things up, I'm only using this, but I'll show you the formula if you need to see it. I figure a lot of people are going to be doing it this way. So that should be 84, but yeah, I can set the formula up for you if you need that. Should be 84. All right, got it. Daily lotteries conducted with 3 winning numbers out of 59 without duplication. Yeah, so there's making it clear we're not repeating the numbers. How many different combinations winning numbers are possible? Let's think about if will the order matter or not on this one. Order generally doesn't matter on lottery numbers, unlike a race or something like that. So if you have the right numbers, you're generally going to win in a lottery. The order doesn't matter. Oh goodness, if you think about like the lotteries we have now, like the Powerball and all that kind of stuff, if order mattered, people would never be winning it. It would probably get up, jackpots would get over $1 billion on probably often, a lot, because it would be so hard to hit it. It's already hard enough to hit it now, but if the order mattered, holy cow, it would just go time after time without getting hit, to build up to really rude numbers. Let's see. This will definitely not be over. So 59 total, selecting 3. So it should just be 59, choose 3. So it kind of looks like these homework problems are sort of set up in the kind of the order of the counting rules. So you see these ones toward the end are the combination problems. And then before these were permutation and the other stuff before that. 32,509. Okay, well, finishing a little early in the notes gave us more time to do more of these, I guess. So that never hurts, I guess. Even though you're probably getting sick of this. We're done. I'll do the next one, then I was going to field questions after that, but we're basically done. 15 exercise bikes. Owner wants to display 4 of them at a fitness expo. How many can be selected? So nothing indicating order should matter here. So but it's pretty wild though, isn't it, using this calculator that man, a lot of these. Oh, what am I doing? 15, Matt, trying to talk and I'm screwing this up. And you see what I'm doing here, a lot of these problems, you're not even having to write anything down even, are you? I mean, you can just sit on, you know what number goes where, bing, bang, boom. I haven't written any of this down on the screen or anything. So 1365. So who's going to go? I mean, not the second we're done, but so somebody going to. It's almost 10 to doing tonight, isn't it? I'm not saying you should, but I mean, you feel like you sit down and knock these out right now while they're fresh. Now, obviously, the Bayes problems are going to take a little more work, but this section, I bet you'll be able to knock out pretty quick. Excellent. All right. Well, I'm just going to open the floor to any questions, and other than that, I think that's going to end this presentation, but I'm not going to cut it, shut it down yet until we see what, let's see if I'm just going to come back and see if I see any kind of chat questions or anything. Okay, I don't see anything in the chat, so we'll give you a couple of minutes if there's anything you'd like to ask or anything other than that. So I'm just going to wait here and we'll see you next week. Looks like there's 3 people.
Thank you, Professor.
Okay, you're very welcome. Looks like there's 3 people here with me. We'll see. Like I say, no problem. If you got something, I'll be happy to help you. I'm not trying to get rid of you.
Professor?
Okay, I'm looking at the chat here. Let's see it. Okay, that's you. Thank you and have a good night. You too. Good evening, everyone. All right, I'm listening while I'm typing this in there. Good night, all. All right, I'm listening.
Yes, Professor. I'm trying to do number 8 in homework, but I don't know. I'm kind of confused.
Where we just were, number 8?
Yeah, number 8.
All right. So what? Well, you're going to see different numbers than me or whatever, obviously. So.
Yeah, I see different numbers. Hold on. It says, how many different ways can a senior project manager and an associate project manager and a technician be selected for an analytics project if there are 9 data scientists available?
Oh, it's got a 3rd position on yours?
Yes.
Oh, okay, then you'll choose 3 then. Okay, I didn't realize that's interesting.
Yeah, that's why I was confused because I was trying to do the way you showed me, so that's why I wasn't getting the right answer.
Oh, I didn't know. Okay, I didn't see that. I wish that would have come up on this one. I wish it would have been brought up. So from based on what you just said, then if it's 9, it'll be a permutation still. It'll be the P, but it'll be 9 choose 3 because there's an extra position on your problem.
Oh, okay, okay. I put 2, so that's why I didn't get the right answer. So
Yeah,
it's
yeah. Because
nine
I
nine
was I was only
Okay.
saying 2 based on the problem I had on my screen, but I didn't have that technician. So if it throws an extra thing in there, then yeah, you got to include that. So yeah,
Oh, okay,
yeah,
okay.
whatever. That's kind of weird. Usually it doesn't change wording around that much, does it? I'm going to try a similar question here and see if that pops up.
Yeah, because I didn't know how you like how you figure out if it's 2 or if it's 3.
It's
So
just
that's why I was
it's
confused.
just how many positions. Um, like the one I did earlier with whatever the president, vice president, and whatever secretary, whatever. I've done problems like those in the books where it said vice president, president, vice president, secretary, treasurer. So if it lists 4 things, that means you're choosing 4. So that is really weird that this one does not mind. It shows 3, doesn't show that technician. Yeah, you see, I got it right when I did it for this one because it was 2. So yeah, if it also says technician, then that's just choosing a 3rd thing out of your total. So did you try? Did that work? Did P93 work?
Yeah, let me see and let me put the answer in and see if it works.
Yeah, assuming you haven't changed it to where it's different numbers or whatever. But it.
Okay, yes, it did. Thank you.
You're very welcome. Well, that is really strange. I mean, it wasn't hard for me to clarify for you. It was easy to explain. But I'm just more surprised that why didn't my problem have the wording where it showed, also technician. That's weird that it didn't show it that way from my point of view too. So, well, okay, that's good then. So hopefully, if somebody that watches this, if they stick around all the way to the end, this will be a good explanation for them to hear what I just told you. So.
Yeah, but thank you, Professor.
You're very welcome. No wonder you were confused there. Yeah. So it's whatever they were choosing, just how many different positions there were. So very good. Let's see. Is it just, still 3 people? Okay. All right. Hanging in there. So.
Professor, I had another question. So tonight after 11:59, the exam going to be open, and we're going to be able to see what we got wrong.
Well, wait. Not automatically. I may wait until tomorrow to open it, but you're asking. I mean, you have to if you haven't taken it yet. Yeah, you got to start it before 11:59, and then you'll have the amount of time. I'll probably wait until. Well, I don't necessarily want to do that at 11:59 because people are still going to be in the test. So I'll probably just do it tomorrow then or whatever. So. And I'll make an announcement.
Oh, I've taken a test already.
Yeah. I'll make an announcement. You'll see a Blackboard announcement saying, so that we don't have to keep checking it all the time. When you see a Blackboard said exams now viewable, probably tomorrow sometime. It won't be but it won't be exactly like if you're wondering if it was like automatically going to pop up at 11:59. I have to make it pop up, and I'll do it tomorrow. So, and I'll announce it. So,
and also, I was reading it. I was reading your syllabus, and it says something about if you pass 3 all of the exams, you don't have to take the final. The final is optional or something like that.
Yeah. But
if you pass all 3 exams.
But that Excel project that major Excel project is not optional. The final is. Somebody was asking me the other day if the final exam can replace that Excel project. Absolutely not. But what you said is correct. You can take that final if you want to. It can replace an exam or choose not to. It'll be completely your choice.
Oh, okay.
But it will not, that will
right, thank
absolutely,
you.
that is, yeah, it will not be required. So, but they don't jump over and final exam. That was a nice try by that person, but the final exam does not. Can I take that instead? Hey, if it was up to me, I would have given a final exam instead of that project. But I had no choice.
Professor, can you do number 7 on homework?
Same section?
Yeah, same section, number 7.
All right. So was that okay? Let's say I'll have about the exam. I said I'll put an announcement in Blackboard. So sometime tomorrow, and it'll stay up for the remainder of the semester. Not just like, okay, you better. I'm only leaving it open for 30 minutes. No, it'll just stay open the rest of the way. So I'll open it up sometime tomorrow. I know if you already took it, you're probably excited to see it. I understand. But like I said, some people, if they don't start it till like 11:30, they've got until whatever, however long, 2:30 to take it. So who knows? I might still be awake then. I might not be awake then. I don't know. But I'll just do it when I wake up tomorrow sometime. So, all right. So 13 rows, 13 vegetables. Each vegetable is one and only one row. Should just be 13. What did you try?
I don't understand how to do this, so that's why I was asking.
Okay. So you didn't type anything in there and like miss it or anything like that, did you?
No, not yet.
Looks like it should just be 13 factorial. Or is it a combination of 30? It's probably, let's see, 13 rows. So how many ways? Each vegetable is allowed one and only row. So probably just 13 factorial. I'll try that. I'll see what, you may have different numbers, but I'm going to try 13 factorial and see if that's right.
Okay.
Let's see. Because it does seem to apply that by saying each one, they're trying to imply that there is an order to it there. So that's going to be a pretty big number.
Yeah, it is.
62270. 62270. 20,800. Yeah, I hope this is right. Yeah.
Okay, so mine says 9 in the homework.
So
9.
You just do 9 factorial.
Yeah, 9 factorial.
It's because I say it's 13 and 13. You can do a permutation. I'll show you it's the same number here. This is the same number as if I would have done 13 permutation 13 is the same number. But whenever they're the same number, it's always equal to the factorial anyway. So either way is right. If you did 13, 13, that's fine. It'll be the same answer. Same answer. So anytime that a permutation, they're both the same number, it's just the same as the factorial. So yours will be yours will be 9 It's whenever these numbers are different, that's when it generates, using the formula or whatever. But so if yours says 9, it should be 9 factorial. Then you should be should work.